Okay, young people, today we're going to talk a little bit more about the history of the atom. So over time, we have seen the atom change and the form that we see change overall, and how we view the atom and how we see the atom. And so today we're going to be talking a little bit more about how this thing that is pretty complex and yet makes up everything in the world works. So the first person that we're going to talk about today is in 400 BC in ancient Greece. Democritus, there he is, was the first guy to believe that everything was made of small particles. And each particle would vary in size depending on what the type of particle was, but everything was made of these small particles. And he called those particles, this was his view, let me go back for a second. This was his view, okay, and he called those particles Atmos, meaning indivisible, basically these things that we couldn't divide any further. So the Greeks believed in the four fundamental elements of nature, that's fire, earth, water, wind. And so the problem was that there were philosophers of the time that had just come up with these ideas, and it made more sense to the people, and so Democritus was not believed. So there was little evidence to support what he was saying. It was just a thought problem for him. So Atmos stopped existence for more than 2,000 years. Then we go a little bit further into history, a little bit closer into history, to the Alchemists. Alchemists were actually the chemists of the Middle Ages. They bridged the gap between what the Greeks believed and the observations that they were making with their work changed everything that we really knew about what we were doing. Basically, they were tasked to change metals into gold. Okay, these are some symbols that alchemists use for different things. You notice we start out with fire, water, air, earth. Some of the same things that were taken from the Greeks. And then we start seeing a little bit more alkali, alum, aluminum, antimony, arsenic. Some of those things sound very familiar. Boron, bismuth, brass. And we see that they were creating symbols to represent those things. Then we come to the age of the Enlightenment, and Joseph Priestley and Anton Lavoisier are very, very big parts of this, because their experiments lead to some ideas that gave this man, John Dalton, in 1803, the name of the father of modern chemistry. Okay, Dalton says that all matter was made up of tiny spheres that he called atoms, very much like the word that Democritus had used. And he said that atoms were indivisible and indestructible. And based on Lavoisier's law of conservation of mass, that's why he said this, because you couldn't destroy them. Elements were distinguished by their mass. And he said that atoms of the same element have the same mass, and atoms of different elements have different masses. He didn't take into account something that we know today about isotopes. Based upon Priestley and Dalton's experiments with mercury and oxygen, this is what he based everything on. He had experimental evidence along with Joseph Priestley that helped determine this. So atoms in a chemical reaction then combined in whole number ratios to form compounds. And again, based upon observations of the chemical reactions that he had done, this was called the law of definite proportions, because he saw that things were reacting exactly the same all the time. But he also knew that sometimes you could take two of the same atoms and you wouldn't get the same ratios depending on the kind of reaction. And he called that the law of multiple proportions. So he's starting to think of this idea of how they come together. Well, Dalton's atom, his model of the atom was accepted because he had experimental evidence. So then we go on to the discoveries. So we have Michael Faraday, who comes in and who changes the way we look at atoms, because remember, they were indivisible and indestructible. And Faraday discovered that there may be an electric component, because he could place electrodes in water and he could collect elements and notice that there was a certain way those elements were collected. Then we have William Crookes, who came up with something called the cathode ray tube that he could fill with gas and it glowed as electricity was passed through it. And the cathode ray tube will come back into existence. So then we have Thompson. And Thompson's discoveries come after both Faraday and Crookes. And Thompson found that the atoms, in fact...
Okay, this is a cathode ray tube. What it essentially is, it's a vacuum chamber. There are no gases inside this glass tube. The only thing we have are two electrodes. One's called the cathode, the other's called the anode, and a fluorescent screen in the background. It's coated with some type of fluorescent material. When I turn the power supply on, we'll see a beam that causes that fluorescent screen to glow. Looks like a nice straight line, doesn't it? We call that a cathode ray because it emanates or begins at the cathode and shoots across over to the anode. J.J. Thompson was working with cathode rays. We really didn't understand what they were. I mean, we have electricity going in one side and coming out the other, but there's nothing inside to conduct it. It's a vacuum tube. So he decided to apply a magnetic field to this cathode ray. And he found something interesting. We apply one pole of the magnet to this beam and we'll see what it does, and then we'll flip it around and see what the other pole does. This is my favorite part. Can you see what's happening to that beam? What does it appear as though it's happening to it?
It's moving.
It's moving. It's being repelled, isn't it, by the magnet? And we flip the magnet around, and what do you think is going to happen this time? Well, if it's being attracted on one pole, see how it's being attracted there? Let me rotate it so the kids on this side of the room can see it. See how it's being attracted there? And then the other pole, do you see how it's being pushed down? What does that tell me about that beam? It has a what? It has a charge. Let me tell you about the poles of the magnet. The one that pushes it away is the negative pole. So what does that tell you about the charge of those particles? Negatively charged particles. And J.J. Thompson was actually able to do a charge to mass ratio of these particles, and he found that these particles were about 2,000 times lighter than a hydrogen atom. Now at the time that was very profound. What did Dalton say? Are there any particles smaller than an atom? J.J. Thompson just found something 2,000 times smaller than a hydrogen atom. Why is the hydrogen atom and something 2,000 times smaller than it so profound? Because hydrogen is the smallest atom, isn't it? So if we found something 2,000 times smaller, we have found our first subatomic particle. And it's called the electron. That'll work.
So basically, you just saw that experiment. Thompson, after his experiment, proposed that the atom was made of particles that had to be charged. The idea, the first statement that Dalton's hypothesis were that they were indivisible. But if they have smaller particles, smaller things, then that's not true anymore, that atoms, subatomic particles have been discovered. Things that we know are smaller have been discovered. So Thompson called this particle a corpuscle. But later, we know it as electron. So Thompson's plum pudding model was born. And the plum pudding model looks very similar to this, where the orange area is where the positive charge is found, where he didn't know, but he knew it had to exist because when there was no electricity being passed through, there was no light to change and to move and deflect. And then the negative were these pieces that were just kind of sitting in there. Now, I call it something a little different. I refer to it as the butter pecan ice cream model. So if we look at butter pecan ice cream like this, the ice cream would be the positive charge. And where the pecans are found would be where the negative charges are. And you're not guaranteed to have a negative charge everywhere you have a positive charge. But, hopefully if it's good ice cream, you got the negatives where they need to be. So that's Thompson. So thus far, we have that. So I'm going to stop right here and then we'll continue on in a little bit.